A Pew Research survey asked television viewers if it would be very hard to give up watching television. In 2002, 38% responded yes, and in 2018, 31% said yes. Assume both surveys use samples of 200 people. Do a test to see whether the proportion of people who reported it would be very hard to give up watching television was significantly different in 2002 and 2018. So here we're asked to do a test, and we're asked to make a conclusion about a population. So this is an example of hypothesis test problem. In this problem, we have two populations we're interested in, people in the year 2002 and in the year 2018. And we know that for each of these, we're going to need a value for x and a value for n. Now, n is your sample size, and it's said to assume that both years used 200 people. But now we have to find out how many people said yes in each year. In 2002, we know that 38% said yes, but we need to find out how many people that is. So we need to do 38% of 200. If we multiply 0.38 times 200, we get 76. So x is equal to 76. In the year 2018, we know that 31% said yes. So we need to take 31% of 200. So 31% times 200 is 62. So let me just remind you that the way we got these numbers is by doing this calculation, by doing these multiplications. Now we know that the sample proportions were different. One was 38% and one was 31%. But the question we're trying to answer is, do these two samples give us evidence that the population proportions were different? That if we were to ask all television viewers in 2002 and all television viewers in 2018, would those proportions of all viewers be different? All right, so we have to run a test. We'll write our hypotheses. Our null is always that the two proportions are the same. And our alternative, in this case, we want to know if they were different, and so the symbol for different is not equals. We have to show that we can apply the CLT, which means we have to show that n times p and n times 1 minus p are both greater than 10. But we don't have a p to use in the problem, so we need to do what we call make a pooled sample proportion. So for the pooled sample proportion, we look at our data and we add the x's together, 76 plus 62, and then we add the n's together, 200 plus 200, and this is the number that we're going to use for our central limit theorem check. So 76 plus 62 divided by 200 plus 200 gives us a sample proportion, or a pooled sample proportion, of 0.345. And that's what we're going to use for our central limit theorem check. So n, 200, times 0.345, and n, 200, times 1 minus 0.345, in other words, 0.655, you can take out a calculator or use your good number sense to show that those are both greater than 10. Notice that we only had to do one line because both samples have a size of 200. If one of the sizes was different, we would have to show the central limit theorem for the other sample size as well. Okay, now we're going to find our test statistic and p-value, and we're going to find those using StatCrunch. So let's record what we have. In the first year, it's 76 out of 200, and in the second one, it's 62 out of 200. And we're going to need those numbers for StatCrunch. Okay, so let's go ahead and try. We have stat, proportions. We have two groups with summary. The first group is 76 out of 200. And the second group is 62 out of 200. And we're doing a hypothesis test, and the symbol in our alternative hypothesis is a not equal sign. So everything looks good. All right, so here's our test statistic, 1.47, and a p-value of 0.14. So that's a large p-value. That's not an unusual sample. So we have a test statistic of 1.47 and a p-value of 0.14. So what that tells us is that these differences are not unusual. So we are not going to reject the null hypothesis. And now we have to write a conclusion in plain English. So there's not enough evidence to conclude. And remember, we are always writing about our alternative hypothesis. So there's not enough evidence to conclude the proportion who said it would be hard to give up watching television was significantly different. We have no evidence that the population proportions were different in those 2 years. All right. Finally, construct a 95% confidence interval for the difference in the population proportions. How does your confidence interval support your hypothesis test conclusion? Okay, so we're going to make the interval in a second, but remember the key number when you're looking at confidence intervals for the difference of population proportions. In other words, if we were to subtract the population proportions, what are our possible answers? The key number to pay attention to is 0. We just concluded here that there was no difference. In other words, P1 and P2 could be the same. And so if these numbers could be the same, when you subtract them, you could get 0 for an answer. So we're expecting an interval that includes 0. So let's go ahead and see. So we're just going to come here to edit, and now instead of making a hypothesis test, we'll make a confidence interval. So our lower limit is negative 0.023, and our upper limit is positive 0.163. All right, so we'll go ahead and record those. Our interval is negative 0.023 and positive 0.163. Notice that we did get a negative number and a positive number. In other words, 0 is caught in between. So how does your interval support your hypothesis test conclusion? It includes 0. In other words, the population proportions could be the same.